last week Persian came and he solved some question from the book, right? You have to be very familiar with those type of questions. They are similar to what you will see in the midterm and final exam. Now, we were talking about the vector space. We were in the vector space, and now let's have a theorem. You know, if you have a matrix, A belonging to can be written as set of vectors. A can be written in this form. Can you guess what is AI? Can you guess what is like A1, A2, or AN? A is a matrix. So what should be each of these A's in order to make this one look like a matrix? Each of them should be a column vector, right? It should be a column vector. But what should be the number of elements that we have inside the column?
And that would be N.
M.
Sorry, M. Sorry.
M,
Yeah.
because I'm a row.
Yeah.
So this is a column vector in Rm. Then, now why we write it like this is that then the range of A is spanned by these ones.
This isn't the same thing as column space for
Yes.
Yes?
Now, let's have this one. Let's have this set of vector, a set of non-zero vectors where Vi belongs to Rn. Then, so look, we have the set of these column vectors. Then the set is said to be orthogonal if so. What do you think? What was the geometric from, let's say, high school geometric, like very simple geometric? When we say that two things are orthogonal, what does it mean?
90.
They are perpendicular to each other, right? They are perpendicular. So when let's go from high school to the first year of undergraduate, or maybe like end of high school in the physics. When we had two vectors and they were perpendicular, how could we understand that two vectors are perpendicular?
The cosine of the angle should be.
Very true, but we were doing something with the vectors and we were checking.
I think in a product is equal to
The
0.
dot product would be 0 because the cosine,
cosines.
we have cosine 90 in there, like, right? So let's generalize it now. If I have lots of vectors, in order to see that they are perpendicular to each other, what do I have to check?
Just the angle probably, or the product is 0.
Yes, I have to check all the dot products and they have to be 0, because if the dot product has 0, it means they are perpendicular. So they said to be orthogonal, perpendicular to each other, if Vi Vj is equal to 0 for all i's and j's are not same. What will happen if I and j are the same?
It would be 1.
No,
No?
it will be a number.
Yeah.
It will be a number. Now, 1 is a very special
Yeah,
number, so
orthonormal.
we say that, and they are orthonormal if we have Vi Vj, okay, this is the dot product, is equal to delta Ij, where delta Ij is equal to 1 if I is equal to 1 if I is equal to j, and is 0 if I is not equal to j. So as Donna said, if this multiplication is 1, definitely they are orthogonal. I mean, if I and j is equal to each other, but we call it orthonormal. In general, orthogonality is not necessarily orthonormality, but orthonormality means they are also orthogonal. So let's get back to this. Okay, I'll have to slow down. So in RA, we understand that RA will be spanned by orthogonal or orthonormal vectors if the columns of A are orthogonal to each other, right? Or orthonormal to each other. Now let's do a very simple example, and then I will ask a question. I mean, this was good, like we were linking it to the column space, or from the before, we tried to see the bridge, how we are generalizing stuff. So, example is, check the orthogonality and orthonormality of the following sets of vectors. And the first one is, we have this set, -3, 5, 7, -4, 1, 1, sec B, 2/3, 2/3, 1, -1 over root 2, 1 over root 2, 0. Yes? The first one, is it orthogonal? What does the orthogonality means? Orthogonality means that if I have any vi multiplied by vj, it should be 0 if I is not equal to j. Let's check in here. Vi multiplied by vj means that element-wise multiplication and addition. So it will be 3 multiplied by minus 4 plus 5 multiplied by 1 plus 7 multiplied by 1, which is equal to 0. So, and we don't have any other vector to check. If it has 3, we have to check for all the combination. So it is orthogonal. Now orthonormality, what does orthonormality means? It has to be orthogonal. And if I is equal to j, in other words, if I pick one vector and I dot product with itself, I have to get 1. Let's see. Let's start from the first one. Let's say v1 dot v1. What do we get? We get 9 plus 25 plus 49, which is definitely not 1. So it's not orthonormal. Here, let's see the orthogonality. Vi dot vj. We have to check it. So if we do it, we will see that we have minus 2 over 3 root 2 plus 2 over 3 root 2 plus 0, which is 0. So it is orthogonal. Let's see for the orthonormality. Let's say v2 dot v2. We get that it's 1 over 2 plus 1 over 2 plus 0, which is 1. So is it orthonormal?
Yes.
No, we have to check for all. We have to check for all. Let's see v1 dot v1. It will be 4 over 9 plus 4 over 9 plus 1, which is definitely not 1. Remember, if you find one example which is not equal to 1, it's enough to say not orthonormal. But if you find one of the examples which is 1, is not enough. You have to check for all. So it's not orthonormal. Now, we understand that vector vi dot vector vj is actually vi transpose vj, right? Otherwise the multiplication cannot happen. Now, in continuation of this example, I have a question. Given that are orthogonal, represent the orthonormal set which is created by aforementioned vector set. In other words, if v1 till vk are orthogonal, what do I have to do in order to make them to be orthonormal also? Do you have any suggestion? This is actually a theorem. And the theorem is this. If you ignore this part, then is orthonormal. Now, let's define a new term, orthogonal complement. Is it obvious to see it? Because if we are picking up one of the vectors, vi square root of vi transpose vi, and we dot product it by itself, you know that dot product means that this is transpose. So what happens in the numerator, we have vi transpose vi. Here we have two of these from multiply by each other, which will be vi transpose vi, which is 1. Right? So let S be the subspace of Rn, then the orthogonal complement of S is defined as this set, which we represented with this symbol, orthogonal complement, to be a set of vector in Rn, which V transpose S is 0 for any S belonging to R S. So orthogonal complement means I have this vector space, just look at it for a few seconds. I have this vector space and I want to know what is the orthogonal complement. Means that all the vectors, which any of them is orthogonal to this vector space that I have. So these sets of vectors is called orthogonal complement. So what is the characteristic it's carrying is this, that they are orthogonal to the S and we are represented as S orthogonal. Now, we understand that we cannot have, if a vector is in S, it cannot be in V, right? If a vector is in S, it cannot be in V. Why? Because this is a vector in S, the vector in V should be like this, right? Because they have to be orthogonal. But what is the intersection of V and S? So if you look at all the S's and all the V's, they have one intersection. Do you know what is that intersection? In other words, find a vector in S which is also in V and it satisfies the condition that we have. Hassan? Hassan, look, this is the equation. Tell me a value of a vector. Tell me a vector which is the vector transpose of itself will result into the zero. In other words, it's also in S, it's also in V. The intersection, what do you say? What did you say? Nothing. I heard someone said something. I mean, I said the answer. The intersection must be the origin. So the intersection of V and S will be origin, which is 0 multiplied by 0, transpose 0 multiplied by 0 is 0. Otherwise, they cannot be orthogonal complement if a question to Dana. Is S orthogonal kind of, let's say, unique?
I think no.
It's not. And in order to find the S, in other words, we have to solve these sets of questions for non-trivial solutions. Non-trivial means that we are excluding the origin, so we can find it. So let's do an example. For 3, 5, 7 minus 4, 1, 1. Find in order to find, we should find the non-trivial solution to, we should find a non-trivial solution to this. 3, let's say x1 plus 5x2 plus 7x3 is equal to 0, and minus 4x1 plus x2 plus x3 is equal to 0. So we know that 0, 0, 0 is definitely one answer. So another answer can be how can I find the other answer? Do I have a unique answer? No. Why?
Because you got
Three unknowns, 2 equations, so that's definitely a parametric solution. So if you want to find the answer, I can say that, let's say for instance, I don't know, x3 is equal to 1, and then I will have this sets of equation 3x1 plus 5x2 is equal to minus 7, minus 4x1 plus x2 is equal to minus 1. Do I have a unique solution in here?
Yes.
Yes, two equations, two unknowns, and from here I find that x1 is alpha, for instance, x2 is beta, so my S orthogonal complement is alpha beta 1. I mean, you have to calculate it. You have to calculate it. I think the solution will be alpha is minus 2 divided by 23, and beta is, I guess, minus 31 divided by 23. Now, if the dimension, what is the dimensionality in here? 3, isn't it? Right? So we understand that if we want to find S complement as a set of vector, like a vector space, we need to have at least one missing dimensionality. In other words, I have 2D, which is being spanned by this set of vectors, and there will be one plane with lots of vectors which is perpendicular to these ones. So if I had 3 here, I could not find sets of vectors. I could find only one intersection point, which is another case. Now, this orthogonal complement has some very important properties. And the properties are this. Actually, this is a theorem. My markers are finished. Let S be a subspace, subvector space of Rn, then we have these ones. 1. S orthogonal is also subspace of subvector space of Rn. What was this symbol?
Direct sum.
Direct sum. Direct sum means that we put the elements together, but if there is an element which is intersection, like common, we put them only once, not twice, right? So if I do that, what do you expect that we get?
Zero probably, or no.
These vectors that we have, direct sum with this vector, do we get 0? What do we get? We get the Rn. We get the Rn. It was easy to understand in the sense that the vectors in here are not in here, and the vectors here are not in here, right? And when we put them together, we will get the whole Rn. Third one. What is the orthogonal complement of S?
S.
S itself. the subspace of S, vector space S, if and only if the orthogonal complement of S is a subsets of vector space of orthogonal complement of R. Five and 6. R plus S orthogonal complement is R orthogonal complement intersected by S orthogonal complement, and R intersected by S orthogonal complement is R orthogonal complement plus S orthogonal complement. You might have remember all of these ones from the set theory in discrete mathematics in undergraduate, because it's just like set R union S complement, the De Morgan's rule, is R complement intersected by S complement. Do you remember these formulas? Like set A intersected by set B complement is A prime union B prime. It's got the De Morgan rules. So we see that actually we have it in the general form for the vector spaces. The proofs are available in the book. You can have a look at them. You can have a look at them. For us, it's more important to use these in order to go ahead and get further conclusion in other theorems. So let A be from Rn to Rm, so it's a linear transformation. Then what is NA? Null space of A. So the orthogonal complement of null space of A is actually range of A transpose, and orthogonal complement of RA is null space of A transpose. Now we have two definitions, and after these two definitions we get back to these two things that we have written, and we show them in a graphical form. V belongs to R and AV is equal to 0. Look, AV is equal to 0 is sometimes called, what do we call this one? What are V's? You know, we had this one before. This is a famous definition. It's the definition of null space of A,
Yeah.
right? So, but sometimes it is called right null space. Look, because it's from the right side. These are the right side of A. Of W's belong to Rn in a form that W transpose A is equal to 0 is called the left null space of A. Why it's left? Because look, W is multiplied from the left. However, W is considered as not right null space of what? W is left null space of A. But I can say that at the same time that W is the right null space of
A transpose.
A transpose, excellent. Because if I transpose both sides, what I get is A transpose W is equal to 0, which means that the W is is right null space of A transpose. So I can write it in this form. The right null space is NA and the left null space is NA transpose.